In Chapter 10, we are creating new functions by combining multiple functions together. In 10.1 and 10.2, we are combining functions using our traditional operations, adding, subtracting, multiplying, and dividing. In 10.3, we are going to create new functions by taking one function and placing it inside another function, creating a new function called a composite. For right now, we're going to concentrate on adding and subtracting functions together to create a new function. We are going to look at how to graph a combined function. We're going to look at writing the equation and also doing some evaluating. Let's start with the Explore below. We are given f at x, which is root x plus 2 plus 3, and g at x, which is negative x squared plus 5. We are going to complete the table of values that is started for us below for f and g at x. This means that we are going to take the table here. We are provided with some x values. And to start, we're going to take those given x values and we're going to plug them into f at x. And we're going to see what the corresponding y values are. Let's start with negative 3. So this is going to be equal to negative 3 root negative 3 plus 2 plus 3. Now negative 3 plus 2 is negative 1, and the square root of negative 1 does not exist. So even if we try to add 3 to it, that y value is still not going to exist. So I'm going to put DNE, which stands for does not exist. Let's plug in the negative 2. So negative 2 plus 2 is 0. The square root of 0 is 0. 0 plus 3 is 3. Plugging in negative 1. Negative 1 plus 2 is positive 1. The square root of positive 1 is positive 1. Plus 3 is 4. Plugging in 0. 0 plus 2 is 2. The square root of 2 is irrational, so I'm just going to write it right now as root 2 plus 3. For 1, we're plugging in 1. So square root of 1 plus 2, which is the square root of 3, that's also irrational. So for now, I'm just going to write it as root 3 plus 3. And then for 2, we are plugging in 2 plus 2, which gives us 4. The square root of 4 is 2. Plus 3 is 5. And finally, plugging in 3, we get 3 plus 2 is 5. The square root of 5 is irrational. So as an exact value, root 5 plus 3. And let's go ahead right now and let's get the decimal approximates for those three. We have them right here. So root 2 plus 3 is about 4.4. Root 3 plus 3 is about 4.7. And root 5 plus 3 is about 5.2. So I'm going to put those decimal approximates here. So equals approximately 4.4, equals approximately 4.7, and equals approximately 5.2. Just double check that I put those right. Yeah. All right, now let's do the same thing. I'm just going to change colors and we're going to do the same thing for g at x. We're going to take those given x values, plug them into g at x and get the corresponding y values. So plugging in negative 3, that means we get a negative 3 squared plus 5. Negative 3 squared is positive 9 times negative 1 is negative 9 plus 5 is negative 4. Plugging in negative 2 squared is positive 4 times negative 1 is negative 4 plus 5 is positive 1. Plugging in negative 1, so we will have negative 1 squared plus 5. Negative 1 squared is positive 1 times negative 1 is negative 1 plus 5 is positive 4. Plugging in 0 squared is 0 times negative 1 is still 0 plus 5 is 5. Plugging in positive 1 squared is 1 times negative 1 is negative 1 plus 5 is positive 4. Plugging in positive 2 squared is 4 times -1 is -4, plus 5 is 1. And finally, plugging in 3, 3 squared is 9, times -1 is -9, plus 5 is -4. So there are the y values for g at x. Our next set of instructions says sketch the graphs of f at x and g at x on the set of axes shown below. We're going to use different colors, so we'll use blue for f at x and red for g at x, and then state the domain of each function using set notation. Okay, so we're going to start with, I'm going to start with g at x just because I have the pen ready to go here. So at -3, we are at -4. So that'll be down here. That's tough to sketch. I'll just skip that one. At -2, we're at +1. At -1, +4. 0, 5. 1, 4. 2, 1. And then 3 is going to be down at -4 again. But that's enough for us to connect the dots. We can see that it is a lovely quadratic. And we are also asked to write the domain of g at x. So let's put that here. So the domain for g at x in set notation is going to be the set of all x such that x is an element of the reals. Let's go ahead and plot f at x as well on the same set of axes. So we have at -3, it doesn't exist, so we can't plot that. -2, we're at +3. At -1, +4. At +1, or sorry, at 0, we're at 4.4, so we'll have to sort of approximate that. +1, we're at 4.7. At 2, we are at 5. And at 3, we're at 5.2. So connecting the dots there looks like a radical function. There we go. There's our graph of f at x. So our domain of f at x, we can see it starts at -2 and opens to the right. So the set of all x such that x is greater than or equal to -2. Otherwise, x is an element of the reals. There's our domain. Okay, let's move on. Given that h at x is equal to f at x plus g at x, so we're going to create a new function by adding together the two functions we have. We are going to use the table of values that's up above, and we're going to add the y coordinates for f and g in order to complete the column for h, and then we're going to sketch h at x. So what we are finding right now is what happens when we take these two functions, f at g, and add them together to create a new function, which would be h. So let's grab green. Now, so at -3, I'm not plugging the x values into anything. I'm taking our two y values and adding them up. So does not exist plus -4 still does not exist. 3 is our y value from f at x. 1 is our y value from g at x. 3 plus 1 is 4. We have 4 and 4 for the next point, which would give us 8. This one, approximately 4.4 plus 5 is about 9.4. About 4.7 plus 4 is 8.7. At x equals 2, the y value for f at x is 5. For g at x, it was 1. So for h at x, it's 5 plus 1, which is 6. And then we are going to add the 5.2 and the -4, which gives us positive 1.2. So now we're going to graph h at x. We're starting at an x value of -2 and a y value of positive 4. So -2, positive 4. And then at -1, we're at positive 8. Then we're all the way up at 9.4. So I'll just sort of guesstimate where that is, somewhere up there. And then down at 8.7. And then at x equals 2, we are at 6. And finally, at x equals 3, we are at 1.2. Okay, so we can tell it sort of has a quadratic kind of look to it, but it doesn't, it obviously just starts here, which is interesting. And it makes sense because the function, if this green function comes from the adding of these two functions, it can only exist where these two functions exist. So it makes sense that the green function doesn't start until right here because the blue function, f at x, doesn't start until right there. Let's state the domain of h at x. So we just actually ended up talking about that. The domain of h at x is going to be the set of all x such that x is greater than or equal to -2. Otherwise, x is an element of the reals. And it's because this is where both f at x and g at x exist. So we can't have h at x exist unless both f and g exist. And so it takes on that domain where they overlap. And there's our graph of h at x. So we just found our first combined function, and we found it by taking two functions and combining them together using addition. So let's talk a little bit about what we did. Let's do a quick summary. New functions can be can be created by performing operations with functions. To combine two functions, f and g, we can add or subtract as follows. Let's talk about some notation. So here I have h at x equals f plus g at x. And then below it, I have h at x equals f at x plus g at x. These two notations mean the exact same thing. It means you're taking two functions and adding them together. Sometimes we write it as f plus g at x. Sometimes we write it as f at x plus g at x. They both mean the same thing. Similar with subtraction, if we are creating a combined function by subtracting two functions, we can write it as f minus g at x or f at x minus g at x. They mean the same thing. It means we are creating a new function by subtracting two functions. To find the domain of a combined function formed by the sum or difference of two functions is the domain common to the individual functions. So let's highlight that. Is the domain common to the individual functions? What that means is we need to determine the domain of one function, the domain of the other function, and then decide where those domains overlap. Decide where both of those functions exist, and that becomes the domain of your combined function. The range of the combined function can be determined using its graph for the most part. We're going to find that sometimes we can analyze the function as well to get the range without graphing it, but most times we will have to graph it. And then finally, to sketch a graph of a combined function, add or subtract the y coordinates at each x value. My suggestion is to do exactly what we did above, and that is to make a table of values, get the y values for one function for your f at x, get your y values for g at x, and then take those y values and either add or subtract to get the y values for h at x. Let's go ahead and try some examples. In example 1, we are not given the graph of two functions, but the equation of two functions. Given f at x is equal to 2x squared minus 7x plus 6, and g at x is equal to x squared plus 3x minus 1, determine the simplified equation of the function f minus g at x. Let's remember that f minus g at x means the same as f at x minus g at x. And when we are doing any sort of equation writing, we're going to be really careful about what we write and making sure that we use brackets when we substitute for our functions. So h at x is f at x minus g at x. So let's start by writing f at x. It's 2x squared minus 7x plus 6 minus g at x, which is x squared plus 3x minus 1. And notice I'm taking care to put each of those functions in brackets. When I remove the brackets, h at x equals, nothing much changes with our first function, but what we have to remember is with the second function, when I remove the brackets, that negative gets distributed to every term of that function. So it becomes minus x squared minus 3x plus 1. And now we want to simplify h at x by collecting like terms. 2x squared minus x squared leaves us with just x squared. Negative 7x minus 3x is negative 10x, and 6 plus 1 is 7. There is our simplified form of h at x, which comes from subtracting f minus g. Part B, determine the simplified equation of the function k at x, which is equal to g minus f at x. Let's remember that that just means g at x minus f at x. You might say, well, didn't we just do that? Didn't we just subtract the two? Well, we did in part A, but you'll notice in part A, it was f minus g. Here it's g minus f. Now we should remember that when we're subtracting even just regular numbers, order matters, but you're going to see that order also matters when we subtract functions. So h at x is equal to, let's substitute in g at x again, using brackets, x squared plus 3x minus 1. Let's make sure we get our signs right off the bat. Okay, 3x minus 1 minus f at x, 2x squared minus 7x plus 6. Removing the brackets, x squared plus 3x minus 1, nothing changes there. But here, when we remove the brackets, that negative gets distributed to every term, minus 2x squared plus 7x minus 6. Collecting like terms, x squared minus 2x squared is negative x squared. 3x plus 7x is 10x. Negative 1 minus 6 is negative 7. And we can see that h at x is a different function for part B than it is for part A. So we should probably make a little note here that f minus g at x is not equal to g minus f at x. That when we change the order of the functions, it creates a different function. We're not quite done with this question though. Part C says evaluate f minus g at 3 and g minus f at 2. And I'm going to show you two ways to do these questions. For the first one, f minus g at 3, we already know what f minus g is. F minus g is this h at x here. So this is the same as asking what is h at 3. So we can do that for f minus g. It's this first one up here. So actually, I also need to change this to a k. So this would be h at 3. Let's go ahead and do that. So h at 3 will be 3 squared minus 10 times 3 plus 7, which is 9, minus 30 plus 7. So h at 3, 9 minus 30 is going to give us negative 21, plus 7 gives us negative 14. So that's one way to do that. The second way to do that would be if we hadn't actually already found h at x. If we were just going from f and g, we could also do it this way. A second way to do this would be if we didn't have the combined function already written. So we already know what h at x is. But if we didn't already write the combined function, we could also calculate it by finding f at 3, finding g at 3, and then subtracting the resulting equation. So it would look like this: 2 times 3 squared minus 7 times 3 plus 6 minus 3 squared plus 3 times 3 minus 1. 3 squared is 9, times 2 is 18. 7 times 3 is 21, plus 6, minus 3 squared is 9. 3 plus 3 is 9, minus 1. 18 minus 21 is negative 3, plus 6 is going to be positive 3. Minus 9 plus 9 is 18, minus 1 is 17, and 3 minus 17 is equal to negative 14. So either method works. In this case, because we already found the combined function, it's much easier to just substitute into that, but we could just as easily substitute into the two separate functions and then subtract. Let's do the same thing for g minus f at negative 2. Again, two ways that we can do that. Because we have k at x, we can go ahead and substitute into k at x. So k at negative 2 would be negative 2 squared plus 10 times negative 2 minus 7. This is going to give us negative 4 minus 20 minus 7, which gives us negative 31. But we could do it as two separate calculations as well. So doing this one the second way, we would evaluate g at negative 2 and subtract evaluating f at negative 2. So plugging in, we would get negative 2 squared. Make sure we're plugging that in correctly. So negative 2 squared plus 3 times negative 2 minus 1, that's plugging into our g at x, minus 2 times negative 2 squared minus 7 times negative 2 plus 6. 2 squared is 4 minus 6 minus 1. And this would be 2 squared is 4 times 2 is 8 plus 14 plus 6. 4 minus 6 is negative 2, minus 1 is negative 3, minus 8 plus 14 plus 6 is 28, and negative 3 minus 28 is equal to negative 31. So again, because we already have our simplified equations, we can plug into there. If we didn't have the simplified equations, we could still evaluate by plugging into the individual functions and then subtracting. Example 2, if h at x is equal to f minus g at x, and h at x is equal to root 3x plus 1 minus x squared minus 4, and f at x is 3x plus 1, what is g at x? So this question is kind of like a working backwards question. We know the combined function h at x. We know one of our original functions, g at x, or f at x. We have to find what g at x is. Okay, so h at x is equal to f minus g at x. H at x is also equal to root 3x plus 1 minus x squared plus 4. And that came from taking f at x, which is root 3x plus 1, and subtracting g at x, which we don't know. So we took what we knew, h at x was equal to this function. H at x is also equal to f minus g. We know what f is. Let's solve for g. We're going to start by subtracting root 3x plus 1 from both sides. That actually cancels out this term, and we're left with negative x squared plus 4 on the left-hand side. And on the right-hand side, we're left with negative g at x. Divide both sides by negative 1, and we get g at x is equal to x squared minus 4. So we can actually solve for equations using algebra with other equations. In example 3, we are given the two graphs of f and g, and we are asked to do some evaluation, keeping in mind that when we do evaluation from the graph, we are adding and subtracting the y values. Let's look at the first one. The first one says f plus g at 2. Let's keep in mind what this means. This means f at -2 plus g at -2. It means add the y values at -2. F at -2 is down here at -3. G at -2 is right here at 0. -3 plus 0 equals -3, and that would be our answer. G minus f at -1 means g at -1 minus f at -1. Let's find the y values. G at -1 is up here at +3 minus f at -1 is down here at -5. 3 minus a -5 is like 3 plus 5, which is 8. F minus g at -1 means f at -1 minus g at -1. So we're just going to reverse what we have above, which will be -5 minus 3, which gives us -8. F minus g at +2 means f at 2 minus g at 2. Let's find those y values. F at 2 is way down here at -7. G at 2, again, 0. -7 minus 0, -7. G minus f at 2 means the opposite. G at 2 minus f at 2. So it's going to be 0 minus a -7, which is 0 plus 7, +7. And then finally, G plus f at 2 means G at 2 plus f at 2, which will be 0 plus -7, which gives us -7. So all we're doing when we're evaluating from the graph, finding the individual y values and adding and subtracting them together. So in example 4, we are going to use the graph of y equals f at x and y is equal to g at x to sketch the graph of the combined function h at x, which comes from g minus f at x on the same set of axes. And we're going to state the range of h at x when we're done. So my suggestion is to make a table of values for g, make a table of values for f, subtract those y values to create your new function, and then go ahead and plot it. You could do it right from the graph, but sometimes it gets a little bit dicey, especially when we are subtracting and we are dealing with positive and negative values. So always a good idea to write it out. So we're going to grab some values of x. We are going to get the y values for g at x first, since it comes first in our combined function, and then f at x. And then we are going to create h, which is going to come from g at x minus f at x. So let's have a look at what our values of x is that we want to pick. Now I recognize right away that g doesn't start till 5, so we can only go to 5 there. And the graphs seem to continue on, but I would probably go about as far as 3. So let's look at what the major points are. I'm going to use x equals -5. Let's use x equals -2. We'll use x equals 1, which looks like a good one. And then that's about it that we can see for the graph. So those are going to be our 3 points that we're going to look at and plot. So g at -5 is down at -4. F at -5 is at +5. So h is going to be at -4 minus 5, -9. At 2, g at x is down at -1. F at x is up at +4. -1 minus 4 is -5. And at +1, g is way up here at 9. F is down at +3. 9 minus 3 is 6. So let's plot our new points. -5, -9. So that's going to be way down here. We're just going to kind of guesstimate where it is. -5, -9. So 2, 4, 6, 8. We'll say down here. Okay. And then at -2, we're up at -5. So right here. And then at 1, we are at +6. And then it goes down from there. Now, one thing I do know is at this point right here, where they're the same, that's going to be 0. So this is going to be an x-intercept. Same thing here, because when we subtract those two y values, that's also, so that gives us a good idea of what this is going to look like. So connecting the dots, we have this section here, which comes up like that. Then we have this middle section here, kind of creating a triangle. And then we have the final section here, and then it's going to continue from there. And there is our graph. Again, a good idea. Create a table of values for one function, a table of values for other, and then put them together using that operation. Your job now is to practice some of these questions from your textbook before moving on to 10.2, which is combining using multiplication and division.